Hey everybody, I just wanted to do one more main method example where I go a little slower and where I'm not really sick and rushing through everything to kind of explain just once again what we're doing here and how we set everything up. So here we have an argument, right? Two premises and a conclusion. So the first step of the main method, remember, is everything's already pre-nexed here. So we're golden. We don't need to worry about that. And on the final, I'm going to give you all of the main method questions already pre-nexed. Because I think for some of you, the pre-nexing is harder than the main method. Anyway, so the first thing we do, we take our conclusion right here, and we negate it. Right? And then we move the negation sign through the quantifiers using the quantifier equivalency rules. You can look on the final exam worksheet or final exam rule sheet for those. And we get okay. All we did there was use the same rules that we use for converting Boolean schemata to quantificational schemata. And then we add our negated conclusion as a third premise. Like so. And the reason why we're doing this is there's a technique in logic known as reductio ad absurdum. And how it works is if you have a series of premises, so right, and you have a conclusion, right, or actually wait here, let me set up a more sane one. So if we have P and Q, we have P, the conclusion is Q. Right, so in case you need to satisfy yourselves, do a truth value analysis on the this, and it'll come up valid, right? So these the premises really do imply the conclusion. This will always end up in true, right? And so we have not been doing, I guess, proofs, technically speaking, this far into the course. But if we were doing proofs, one of the things that we could do is we could assume the negation of the conclusion, not Q. And if you're just gonna have to trust me on this, I do not have the time to explain how or why it works exactly. But so if on the assumption of the negated conclusion, remember the conclusion was originally Q, right? If these premises are inconsistent with each other, then we know that the conclusion, our original conclusion Q, has to follow from the premises, the original premises, and that's because if the conjunction of, how do I want to say this? So if this is inconsistent, and it is, it'll always reduce to false, right? And never mind, I don't want to try to explain that. Sorry, this isn't going to be edited. You have to hear me do this live. So what we're doing with the main method here, when we add the negated conclusion, and we try to get a contradiction, we're trying to use this reductio ad absurdum technique as it's known in other logical systems. And we just know that if we add the conclusion to our premises, add the negated conclusion to our premises, and we get a contradiction or a set of inconsistent schemata, we just know that the argument has to be valid. The technical explanation of how all this works is incredibly complicated. So you're just going to have to trust me. But if you've taken another logic class, perhaps you're familiar with that technique of reductio ad absurdum. So here we have added, our conclusion that we have negated and driven the quantifiers, or driven the negation sign through to the right. And so then we're going to generate instances. And what the instances are, so quantifiers imply their instances. We don't have rules for this. And I mean, this is what our instantiation rules state. But what that means is that something like this conditional is true, provided that we obey the restrictions. So if everything's a pi in our universe of discourse, then whatever the object A is, it has to be a pi, right? And, for the existential quantifier, it's a little more complicated. So if there is a pi in our universe, right, then we can pick a letter that we haven't already used. Because when we say that something or there exists a pi, what we mean, we know if that's true that, there has to be at least one thing that's a pi, but we don't know what that thing is. And the reason why we have to pick a new letter is because we don't know that it's like the same thing as anything else in our universe of discourse, right? So we know that something's a pi, but we can't just go around saying that, if we had... on another line, Trump is orange, right? We couldn't say necessarily that Trump is a pi, right? We don't know that. We just know that something is. So we have to pick a new letter that we haven't used before, and we couldn't use T here if we were considering that schema. Because we don't know what we don't know which object is a pi, we just know that one of them is, okay? And so what we're doing here is when we add this negating conclusion, if an inconsistent set of schemata is implied by the conjunction of the premises and the negating conclusion, right, then we know that the argument with our original non-negating conclusion must be valid. It must follow from the premises. And so what we're trying to do is we're trying to use UI and EI to drop these quantificational schemata to something we can do truth value analysis on. And the goal is to get something that's inconsistent because, again, if you add a negated conclusion to the set of premises and that implies something that either is inconsistent or implies something that's inconsistent, then it's just the case that we know that the conclusion has to follow from the premises. So I hope that explains why we're doing this. I know you have to trust me on how reductio ad absurdum works, and the quantifiers implying their instances stuff. I apologize. It's just too much to cover in detail in a class that's an introduction to logic class. It's very advanced, the Quine's explanation of how it works. So what we do here is we're going to, the Roman numerals just indicate where I've started moving into the instances that I'm dropping, or that I'm dropping the quantifiers to. So remember, we should always drop existentials first. So the first thing we're going to do is work on this one. We're going to drop the leftmost one because we have to start dropping the leftmost one, right? And of course, it doesn't really matter which letter you pick here as long as you're obeying the restriction that when we're using existential instantiation, the variable that we're introducing when we remove the quantifier has to be new. Okay? And again, so here we still have an existential quantifier, and we want to drop that before we drop the universals, so we get this. And this is just using existential instantiation on our instance in line 4, okay? And So having done that, for this one, there's not a whole lot of thinking involved here, really. We know we need to drop the quantifiers in lines 1 and line 2 to get something that'll come up inconsistent. And so, what we want to aim for is, since we have to, if we drop the y quantifier here in premise 1, we have to replace every occurrence of y with it, right? And because we dropped these quantifiers to, or the variables bound by the quantifiers in 3 to a and b, we need to find a way of dropping the quantifiers in 1 and 2 using ui and ei that match up with this, and that should give us a truth functionally inconsistent schemata via truth value analysis. So to do that, it's really just playing a little game of match the letter. And because we have this, this here, the x and the y are going to have to be dropped to different letters just because of the restrictions on our rules. And because we have the two different letters here, we should probably try to drop the x and the y here to a and b, which is going to force these y's to go to b, which means that we should then drop these x's to b's as well. So I'll just do that, and you can see what I mean. So let's start with premise 1. So and because we're using universal instantiation, the only restriction is that if we drop a if we drop a quantifier that binds a variable, we have to replace all occurrences of that variable with the same thing. But it doesn't matter if it's free on previous lines for this one. That only matters for existential instantiation. So I'm just gonna work on this one again, drop the next universal quantifier, and I have to drop it to b here if I want this line to match up with this line. And if you don't match up the variables right, you won't get truth functionally inconsistent schemata. So you have to, for simple ones like these, really the hard thing is just matching up the variables in a way that will lead you to something that's truth functionally inconsistent. So just gonna get rid of that y quantifier on line 6, replace the bound variable with a b. Okay, and that is ui on 6. Okay, then only thing left to do is to work on this right here, premise 2, and we have to drop it to b. There's nothing else we can do that would make any sense here, right? Because if we dropped it to say, FCC, right, then we'd have to put that to one letter, and we'd have to put FBB to another letter, and or not FCC. And these two are perfectly consistent with each other, but we want something that's inconsistent, and so we need to try to match up the letters so that we could put, if this is not FBB, right, and this is FBB, then this would be not Q, and those are inconsistent. But they're not inconsistent if they don't have the same variables or letters. Okay, so for premise 2, not FBB, okay? And that's just UI on 2. And there's no shortcut or easy way of ascertaining when you really have a truth functionally inconsistent set of instances. So the only way to test is to do your truth value analysis, and if you do the truth value analysis and it doesn't come out inconsistent, then you've got to try dropping the quantifiers to something else, a different combination of letters. Like I hinted at in the beginning or at the end of the module video for this, there is not and cannot be, we know it as certainly as we know anything we could possibly know. It's as certain as 1 + 1 = 2. A decision procedure like the method of existential conditionals, where you have precise steps or precise instructions at every step for proofs of validity in polyadic quantificational schemata. That's why we're doing this. If we could do everything with the method of existential conditionals, we would. Okay? And so to test, what we test for using our truth value analysis is we make a conjunction with the lines that we think, when conjoined together, would be truth functionally inconsistent. So these three lines. So not FAB and FB. Okay. And if we put in letters, and remember, so FAB has to go to one letter and FBB has to go to a different letter, we would put in truth functional statement letters like so. So not P, because this is negated, and then P or Q and not Q, right? And let's, if we do the truth value analysis on this, it should come out inconsistent. So we assign P to true on the left-hand branch. So this is a conjunction, and we can join them here. It's conjunction of the lines that we think together might be inconsistent. And this is false, right? Because it's conjunction with a false component, right? On the right side, you get true and false, or Q and not Q. And I hope that you will not think that I am being unfair if I skip a few steps here and just reduce this to Q and not Q, which is false. And we know that our argument is that the premises of our argument imply the original non-negated conclusion because this ended in false in both instances. Now, here's the thing about the main method, and this is a consequence of the lack of a decision procedure for it. This is something we know with just as much certainty as, we know that there's no decision procedure. This really is just what it means when we say that there's no decision procedure, and that is that there is no mechanical invalidity test either. And as a consequence of this, if I were to screw up on the final exam and give you an argument where the premises did not imply the conclusion or was not valid, there's no for sure way for you to tell. So this is only a positive test, and it's not always successful, and you cannot, how do I want to say this? You can't, for sufficiently complex ones, you cannot tell, and there isn't a way to tell without asking somebody who's better at this than you are, or having a supercomputer guess and check. There's no way to tell whether or not you just can't figure it out, or whether it's really not valid, right? And that's what makes this kind of hard. But for all the examples, for all the ones I'm giving you on the final exam, you don't need to worry about that. It'll, if you drop the letters and try to match them up in a way that makes sense, it's not that hard. Yeah. So hopefully this helped. Hopefully a little bit more explanation was useful. By the way, our original conclusion, just in case you were following along, you couldn't remember, it was right. And this all together is a proof. It's sort of like a derivation if you did derivations or proofs in another logic class, but it's sort of like an upside down, inside out derivation, I guess. And so this constitutes a proof because our truth value analysis, we've got something that's truth functionally inconsistent that is implied by the original premises and the negated conclusion, that this conclusion really does follow from these two premises. So that's how you set it up, a little slower, maybe a simpler example, and hopefully that helps. Yeah. The ones that this one that I'm just did here is extraordinarily similar to the ones that are on the final exam. It is of comparable difficulty to all of them. Well, there's only one, but I made a bunch of different versions of the test. So anyway, I hope that was helpful. If you're still confused about this, shoot me an email. I can do office hours by appointment before the final. And good luck with your studying.